Alright, today we are moving on to 7.3 power functions and function operations. We're going to start with something that you do know. We have the polynomial 2x minus 5 plus 3 of the polynomials 4x squared minus 2x plus 7. We know the first thing we've got to do is distribute that 3. Nothing's changing to that 2x minus 5. So that becomes 12x squared minus 6x plus 21. Then we want to combine like terms, having our answer in descending order. So we've got 12x squared, 2x minus 6x is a negative 4x. A negative 5 and a positive 21 is going to give us a positive 16. Now we're going to take that simple idea of combining like terms and adding polynomials together and a little bit new approach. So we're going to have operations on functions. We're going to say f of x is 2x plus 3 and g of x is x squared plus 5. So for number 1, when I say take f of x and add g of x, well, this is f of x, our 2x plus 3, and we're going to add that to g of x, which is x squared plus 5. So we're just going to add those two pieces together, which is exactly what we just did in the previous problem. So we're just combining like terms. We've got x squared plus 2x, 3 plus 5 is going to give us 8. And number 2, we want f of x minus g of x. So we have our f of x, which is 2x plus 3. This time we're going to subtract g of x. And when we subtract, we're subtracting that whole quantity, so I distribute that negative. So that becomes 2x plus 3 minus x squared minus 5. Again, we have it in standard form, which is in descending order. So we've got a negative x squared plus 2x. Positive 3, negative 5 is a negative 2. Number 3, we have f of x times g of x. Our f of x is 2x plus 3. We're multiplying that by g of x, which is x squared plus 5. We have two binomials being multiplied together, so we have to FOIL. 2x squared plus 10x plus 3x squared plus 15. Oops, that first piece is 2x cubed. 2x times x squared is 2x cubed. Again, we put it in descending order, so we've got 2x cubed plus 3x squared plus 10x plus 15. So this one we didn't have to actually add any like terms together, we just had to rearrange our pieces. For number 4, now this is where it gets new. We have f of g of x. This is a composite function. This means I'm taking g of x and I'm plugging it in to my f of x equation. When we look at f of x, this is in terms of x. So x is the variable. We are going to plug g of x into f for x. So f of x is 2x plus 3. What this means is we're going to take that x that was in the f of x and we're going to take that out and we're going to put the g of x in. And g of x is x squared plus 5. So that now becomes 2 times x squared plus 5. You are replacing the x. You're not keeping the x there. The x is coming out, the g of x is going in. So that becomes 2x squared plus 10 plus 3, giving us 2x squared plus 13 as our answer. Number 5, we have g of f of x. That means that f of x is going to be plugged into g. So we start with our g of x, and our g of x is x squared plus 5. We're taking out the x and we're putting the f of x in its spot. So our f of x is the 2x plus 3. Now we were squaring x, so we're squaring that quantity. Anytime we do substitutions, we always use parentheses. We are squaring that binomial, which means we are FOILing. So that's 2x plus 3 times 2x plus 3. That's that quantity twice, giving us 4x squared plus 12x plus 9 when we FOIL those two pieces, and then we're adding 5 to that from the plus 5. So that gives us 4x squared plus 12x plus 14. And our last one, number 6, is f of 2. For these functions, we're really going to be working from the inside out. So here we plugged g into f, we plugged f into g, and now we want to first start with f of 2. And we've done these before. We're just, again, going to look at it in a different light. So we want f of 2. That means we take our f of x function, and we're going to plug 2 in everywhere that we see an x. In this case, we only have one spot. So that becomes 4 plus 3, giving us 7 as our answer. But that's only representing f of 2. f of 2 is actually the number 7. So now we have to take that 7 and plug it into the f again. So again, we had 2x plus 3. That x is coming out, and the 7 is going in, giving us 14 plus 3, which is 17. So our f of 2 is equal to 17. Again, whatever's in the parentheses is what's getting substituted in. So we substituted 2 into f. Once we did that, we got 7 as our answer. So then we still had to evaluate f of 7 to get 17. Alright, now we're going to make it a little bit complicated by adding in the idea of domain. So we look at number 1, and if we're trying to consider the domain, we want to think of all the values that we can plug in for x that's going to give us a true answer. Sometimes it's easier to think of terms of what cannot go in. So if I can plug in 0, 0 squared, that's 0, that still gives me an answer. Can I plug in positives? 2 squared is 4, okay. Can I plug in fractions? 1/2 squared is 1/4. I can still get an actual answer. Can I plug in negatives? Well, negative 4 squared is a positive 16 times 6, we've got an answer. If I'm squaring my number, I have no restrictions, which means my domain would be all real numbers. When we go to number 2, we've got 5 times x to the 1/3. Now we know that this is really the cube root of x. So I think about, are there any numbers that you can't plug in? Can I plug in 0? Yes, I can take the cube root of 0, it's 0. Can I plug in positives? Yes. Can I plug in fractions? Yes. Can I plug in negatives? Yes. We do know that, for example, if x was a negative 8, the cube root of a negative 8 is a negative 2. You can take the odd roots of negative numbers. So this one as well is just going to be all real numbers. We look at number 3. We've got 2 times the 4th root of x. Can I plug in 0? Yes, I can take the 4th root of 0. Can I do fractions? Yes. Can I do positives? Yes. But I can't have negative numbers because I can't take even roots of negatives. So this is all non-negative, which means we're just going to write x is greater than or equal to 0. It can be 0, it just can't be negative. For number 4, again, we think about what numbers can it not be. Can it be positives? Yes. Can it be negatives? Yes, I can plug in a negative 1. I can have a negative 2/3 as my answer. The only thing this can't be is that this bottom of my fraction, it can't be 0, because then I would have an undefined fraction. The number that would make that 0 is not 1/3, because 1/3 times 3 is 1, 2 over 1 is just 1. We can't have that be 0, because 3 times 0 is 0. So this is all reals, except x cannot equal 0. And last, again, our fraction cannot equal 0 for the bottom. So I want to find out what number would make that 0. You can either think about it in your head and think, okay, well, this has to be a negative 4, because negative 4 plus 4 is 0. What number would make that a negative 4? Negative 2. Or you can just take the bottom, set it equal to 0, and solve. And we find that x is a negative 2. So in this case, it's all reals, except x cannot be equal to a negative 2. What you want to be careful about is the domain of your answer consists of the x values that are in the domains of both functions being added, subtracted, multiplied, or divided. So when you are considering the domain and range of your problems, it's not just the answer that you have to look at the original functions. And we're going to do this really easily. There's no restrictions here, so this domain is all real numbers. There's nothing I can't plug in. This is all real numbers. Then we look at the answers. Are there any restrictions in my answers? No. So this is all real numbers. Any restrictions? No. All real numbers. Any restrictions? No. All real numbers. And actually in all of these, there's no restrictions. Neither one of our original functions had restrictions, and none of our answers did. For number 6, we're not going to have a domain because we evaluated. A domain is all possible values for x. If there's no x, then we don't have to worry about possible values. Okay, so now we're going to look at some harder problems on the back page. Alright, we want to find the following and state the domain. And don't forget that the answers still have to be in simplified radical form. What I always do, and what I think is a smart thing to do, is always start by identifying the domains of each of your individual pieces. So when we look at f of x, we have the square root of x there. If we have an even root, that means that this has to be all non-negative. So this has to be x is greater than or equal to 0. We have x being squared, which means there's no restrictions. That's all real numbers. Just x plus 1, a linear equation, no restriction. And last, 5x, no restrictions. So far to begin with, we only have the one restriction on the f of x expression. For number 1, we want to find g of h of 3. Again, we start with the inside. We've got h of 3. So we start with that h of x equation, which is x plus 1. If we're evaluating h of 3, we're going to plug 3 in for the x, and we're going to have that become 4. h of 3 is 4. So now instead of finding g of h of 3, we want to find g of 4. And our g of x is x squared minus 4. We're going to take out that x, and we're going to replace it with the 4 that's being squared. 4 squared is 16 minus 4 gives us 12. So g of h of 3 is going to be equal to 12. There is no domain that can be considered there because we evaluated for a number. For 2, we want to find the composite of g of f of x, which means we're going to plug f of x into g of x. So we start with our g of x, which is x squared minus 4. We're going to replace that x. We're going to take the whole thing out, and we're going to replace it with the f of x. So we've got a negative 3, x to the 1/2. That whole thing is being squared. Anytime you substitute, you put the entire quantity in parentheses. And in this case, since it's x squared, we are squaring that quantity. And then don't forget about the minus 4. We are squaring a negative 3. Negative 3 times negative 3 is a positive 9. 1/2 times 2 is just 1x minus 4. Now this is where we've got to be careful. We have to consider the domain. If I look at my new equation, 9x minus 4, there's no number that x can't be. There's no restrictions on my new equation. But I have to consider my f of x and my g of x, my two originals. When I look at f of x, x cannot be greater than or equal to 0, or it has to be greater than or equal to 0 because it can't be negatives. G of x had no restrictions. So from the 3 pieces, the new equation and the 2 original, I have to consider all of those. Since this was a restriction to begin with, it has to be a restriction in the end. For number 3, g of x divided by j of x. Our g of x is x squared minus 4. Our j of x is 5x. I know it's not going to be able to cancel, but I always factor just to make sure. And like we said before, nothing was going to factor. Now we have to consider the domain. Again, we look at the new equation and the 2 original, the g and the j. G had no restrictions, j had no restrictions. But our new equation, or our new expression, has restrictions. We have an x on the bottom, which means x cannot be 0, because if x was 0, the denominator would be 0. So here our domain is x cannot be equal to 0. That's the only restriction that we have. For number 4, we have h of negative 5 minus g of negative 2. So we want to find that h of negative 5. Let's look at our h is x plus 1. We're evaluating it for negative 5, so we take out that x, we put a negative 5 plus 1 in. This is a negative 4. What you want to be careful about here is that we want to evaluate the entire h before we subtract the g. Now we want to evaluate the g. The g is x squared minus 4. We're taking out that x and we're substituting in that negative 2. Again, this is an entire piece. We don't subtract until we've simplified all of h and all of g. So we've got a negative 2 squared, which is going to become 4 minus 4. And 4 minus 4 is just 0. So it's negative 4 minus 0, giving us negative 4 as our final answer. For number 5, we've got j of x divided by h of x. So we've got 5x over x plus 1. We look, nothing can factor, nothing can simplify. So that's literally all you have to do for number 5, and then consider the domain. So we look at j, all real numbers, no restrictions, h, all real numbers, no restrictions, and then we look at our new equation. The denominator cannot be equal to 0, so we look for what value makes the denominator 0, and that is a negative 1. So our domain here is all reals except for x cannot be equal to a negative 1. And our last problem for our video, we have f of x times g of x. Our f of x is a negative 3x to the 1/2 times g of x, which is x squared minus 4. Now we're multiplying these two quantities, so in this case we have to have parentheses so that we're distributing here since g of x is a binomial. We distribute, we get a negative 3x to the 1/2 times x squared, which means we are adding exponents. So that's 5/2. A negative times a negative is going to give us a positive 12 to the x to the 1/2 power. That negative 3 is not connected to that radical. So this is a negative 3, and the square root of x to the 5th power. This is plus 12, and the square root of x. We look here, and we have x to the 5th. It's square root. We only need 2. We have 5. That means we can move 2 of those to the outside with x left over on the inside, plus 12 square root of x. We see that we have like terms here. So we're going to add the coefficients together. And this is a little bit different than the ones that we've looked at. Those aren't like terms. So it's that quantity times the square root of x. Alright, now back to our domain. We look at our original functions, f and g. F has the restriction where it can't be negative. G has no restrictions. So we know that our answer can't be negative. Our domain can't be negative. We look to see if we have any additional restrictions. We still have the even root, so it's still just the fact that it can't be negative. So x is greater than or equal to 0. Alright, and that's it for today.